Hey, welcome back everybody. Okay, last lesson in the radical and rational functions unit. We are looking at today solving radical and rational equations, but not algebraically, just graphically. And we're going to combine some composition and function notation stuff in with this as well. So just to review, a radical equation is an equation that contains a radical and has typically x underneath the radical. A rational equation is an equation that has at least one of the terms in the equation is a rational expression with the variable in the denominator. Okay, the value of the variable which satisfies the equation is called the root of the equation, and we're going to look at finding these. Now, when you hear the words zeros, roots, x-intercepts, really they're all just the same. So to fill this in, the zeros of the function, okay, so if you see f of x equals blah, 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 find the zeros, they're basically saying let y equals 0 or f of x equals 0. The x-intercepts of the graph of the function and the roots of the corresponding equation of y equals 0, otherwise known as the solutions, are the same numbers. Okay, so those all mean the same thing. They just correspond to different words basically, but essentially apply to the same thing. Okay, we're going to skip example number 1 and go straight to the next page. So let's try that. Okay, example number 2. Here we are, a partial graph of y equals f of x, a radical function with an integral 0 is shown. Now what they're saying there when they say an integral 0, so 0 where y is 0, an integral means it's an integer, okay? So where y is 0, here we go. So even though that doesn't necessarily look like it's right at x equals negative 2, because they said the 0 was an integer, it would be x equals negative 2. Okay, so that's what that little direction there is telling you. So then they say state the 0 of the function, and that would be x equals negative 2. State the root of the equation where f of x is equal to 0. So this function set to 0, in other words, where y is 0, again is x equals negative 2. So they're trying to make a point that those are the same. Use the graph to determine to the nearest whole number the solution to the equation f of x equals 3. Okay, so the idea there is we're letting this function that they're given us, and we're making it equal to 3. So if it's y equals f of x, and there's a 3 instead of a y, what we do is go on the graph to where y is 3, go across until we hit the actual graphed function. Go down, read off our x value, and that would be our answer. So the solution would be x equals 7. Okay, you guys try this one out, and yes, you can bring the 4 to the other side first if you like. And so pause your video and see if you can find the solution to the next one. Okay, how'd we do? Did everyone get x equals 14? Good job. Okay, so you isolated f of x first. F of x equals to 4. That means where y is 4, so we went to the graph. Where y is 4, go across until you hit the graphed line, and then down to the x. And there's your answer. Okay, D is a little bit trickier. They throw some horizontal translations in. It says, in each case, explain how to use the graph to determine the approximate solution to the given equation. State the solution to the nearest whole number. So when you look at this, f of x plus 6, think transformations. What's happened if it's no longer f of x, but f of x plus 6? Well, that means your graph moved left 6. So if we take, and it's where it equals 0, right? So if we take our graph and we move it left 6, at what point would this 0 now be? Okay, it was at x equals negative 2. It would now be at x equals negative 8, right? Negative 2 minus 6, because we're moving it left, and that gives us negative 8. There we go. So that means the answer to this would be x equals negative 8. Good. Okay. Why don't you guys try the next one and see if you can figure that one out. Pause your video, and we'll come back and check and see if we have the same answer. Okay, pause your video, please. Nice of me to give you a hard one, right, like that, eh? Okay, so how many of you got x equals 26? If you did, awesome job. Basically what you want to do, this is the y value, right, the right-hand side, because it's f of x equals whatever. So you go on your graph to where y is 5, realizing that we actually want a graph that's been moved right 3. So if we go back up here, we go to where y is 5, and we go across, we would hit a value of x of 23. But if that graph was moved right 3, 1, 2, 3, then that value would actually be x equals 26 instead of 23. So there you go. That's how we got our answer. All right, good job, everyone. Okay, last example, example number 3. Consider the functions f of x, yada yada, g of x, h of x. Okay, determine graphically the solutions to the following equations to the nearest hundredth. Now, before we run to the graphing calculator, because you're all going, yay, don't have to solve it algebraically. Okay, we first have to use, if you'll notice, each of these questions are looking a little ugly. We have to use our skills from previous units to get the right equations first. So, because we can't graph f of x and g of x in y1. So, if you recall, f over g of x is the same as writing f of x over g of x. And then we have minus 5. I'm just going to take that to the other side. Okay, so f of x is 2x minus 3. We're replacing that from up here over g of x, which is x minus 1. And now what we're going to do is we're going to go to the calculator. And in y1, we're going to be putting 2x minus 3 over x minus 1. And in y2, we're going to be putting y equals 5, basically. And where they cross, the x coordinates where they cross is what we're looking for, would be the solutions to the equation. Just make sure when you enter this rational expression in your calculator that you have brackets around the numerator and denominator. Otherwise, you'll only be dividing 3 by x. Okay, let's pause the video, grab your calculator, see if we can get an answer to this. Okay, so this is what we put into y1 and y2. We hit graph, and we should get a graph looking something like that. You can see the vertical asymptote kind of showing up in a weird way, but here is the one graph crossing the other graph. So we're going to go second calc intersect. Okay, now let's see which side. I think we should be on this side, so we're okay by going first curve enter, second curve enter, and then guess enter, and it will find that intersection. And there we go. We get x equals 0.6666. Now, if you don't recognize that, here's what you can do to get that as a nice number. Go here and hit x, quit out of your graph and hit x, and look, there you go. Your calculator stored that in x. Very cool. Then what you want to do is change that to a fraction. So you go math, frac, and it actually changes that to 2/3. There we go. Okay, so our value is 2/3. They did say to the nearest hundredth, so I guess we should write 0.67. But when you can go exact values, it's always better. Okay, let's look at B. We have the root of f of x. So f of x was 2x minus 3, so we'll write that like that, equals, and if you recall, that open dot thing is the same as writing g at h of x, which means in the g function, this one, x minus 1, we're going to sub in h of x, which is x plus 5. Okay, so the g function is x minus 1, put brackets because we're scooping that out, and we're putting in x plus 5. Okay, so we could simplify that a bit if we wanted, or we can just enter it as it is in the calculator. Okay, but we're off to the calculator. We're going to put the left-hand side in y1, the right-hand side in y2, and find out where they cross. So pause your video, go get your answer, and we'll check back in a minute. Hey, are you thinking you did something wrong? I thought so initially too, because this is the graph that I got. Did you guys get this graph as well? Okay, so we know our solution is where these two graphs cross. And do they cross? No, they don't. So as a result, if they don't cross, you would write then no solution. Okay. All right, good. You did not do anything wrong. There's actually no solution. Okay, let's look at C. All right, so we have f over g of x, which is the same as writing f of x divided by g of x. Okay, and f of x is 2x minus 3, g of x, x minus 1. There we go. Okay, on the right-hand side, we've got g of x divided by h of x. And g of x is x minus 1. h of x, x plus 5. And there we go. Let's put the left-hand side in y1 and the right-hand side in y2. Find out where they cross, and we will have our solutions or solution. All right, pause your video, and we'll check back in a minute. Okay, so did you get a funky looking graph? What a mess this graph is, eh? Okay, let's actually make one of our lines a bold line, just so that it's easier to see what's going on here. So we're going to go over to here, hit enter. Okay, now let's graph that. Okay, that's a little bit better. It looks like we have an intersection somewhere over here. And remember, these asymptotes are not actual lines, right? So try to ignore those, these vertical lines here. And then the bold line appears to be crossing the other line somewhere in here. So that's where we want to find our intersection. So we go second calc intersect, okay? And then we want to go for first curve. Actually, for first curve, let's see here. Well, we'll go over to where we want to be. But you could just hit enter and then we'd be fine. But we'll go over close to where we are. Okay, and go ahead and hit enter. Second curve, it jumps to the other equation automatically. Enter, and for guess, hit enter. And it should find, oh, okay, so it didn't. What did I do wrong here? X minus 1, x plus 5. So it doesn't seem to think that those two lines are crossing. I don't know about that. Well, there is another way to go about doing this, and that's taking one of these equations, these rational expressions, to the other side so that we have 0 on one side, and that's sometimes easier. So let's try that. Let's go in here and go to the end, and then go minus, and then put in the other equation. Okay, so let's pause our video, and we'll come back and we'll try that one, see if it works better. Okay, so here's what I did. I basically took this rational expression, brought it to the other side, as in subtract, and then we had it equal to 0. So on the old calculator here, let me just go in here, y equals. So that's what my equations look like. Now, what I've discovered is we could have used what we had. You know what was wrong? Our intersection point was too far left from where our windows were. So we needed to change our x min and well, mostly our x min to something bigger than negative 10, or smaller, I guess, than negative 10. So if we went negative 15, negative 20, that would have been good. So if you just go to Windows, you can keep what you had, but go to Windows and make sure your x min is smaller than negative 10, so negative 15, negative 20, anything like that. Then when you go back to graph and you go second calc intersect, okay, and we're over here and we'll go enter, make sure you're close to that, enter, enter, and there we go, negative 10.52 is one of our intersection points. Okay, now I think there's another one as well, so let's take a look here. Okay, so looks like there's another one crossing over here, so let's go get that one. We would go second calc, intersect. Okay, now we want to move over so that we're past on the other side of those asymptotes here, over in the area where we need to be. There we go. Okay, now first curve enter, second curve enter, and guess. And it should find it. Yes, it did, 1.52. Okay, so there we go. We could have used what we had to start with. The problem was the windows, and our x min needed to go smaller. So yeah, try that. If you think the intersection point is off the screen, especially when it comes to x, your calculator has issues finding it. So you need to basically change your x min or x max. All right, so hopefully this all goes well when you're working with the calculator. I don't know, sometimes there's things that happen that you can't foresee. So make sure you do all the questions and practice, practice. All right, good job, you guys. We finished the unit. Hopefully we'll be ready for the unit test in a few days, and we're good to go. All right, thanks for listening.